Morning, everyone. Okay. Yeah, I hope you people are here. Yes, fine. So, in the previous class, we discussed about the stability of the finite slopes. And there, we discussed about phi u is equals to 0 degrees analysis and method of slices or Swedish circle method. See, I have been discussed all these things in the previous case, and I'll be just giving you a quick review about that. So, in the case of the finite slopes, factor of safety means resisting moment by driving moment. So first in phi u equals to 0 analysis, this method says that the whole soil wedge weight is responsible for the failure. As a weight is responsible for the failure, driving moment is W into X. And resisting moment is going to be resisting force into lever arm. And that resisting force is nothing but shear strength into surface area of the arm. Then from there we can find out this factor of safety. Mind it, I'm not allowing you or asking you to remember the formula. I'm asking you to look over how we proceed towards resisting moment and driving moment. And if it's a canal full supply, then it's a submerged condition. Use gamma as gamma dash. And if I give you canal sudden drawdown case, then you use gamma as gamma sat. In the case of the finding the weight of the soil mass. And then we discussed about the Swedish circle method. In the case of the CD circle method, this is suitable for all type of soil masses. Here, we divide the total soil into slices and we made sure which component is responsible for the failure, tangential component. So driving moment is nothing but tangential force into lever arm R, and resisting force into lever arm. Resisting force means a shear strength in the surface area. So these are the formulas that we discussed at the end. C into L bar plus sigma n tan phi by sigma t. If there is a steady C phase, then you have to take a sigma n minus sigma u. So in the case of the Swedish circle method, side forces are neglected, whereas considered in the Bishop's method, but the most common method is going to be Swedish circle method only. And as I told you, all the methods are trial and error procedures. So what is the meaning of trial and error procedure? I have discussed over here. And then we discussed some of the questions of the GATE classroom practice questions. These are the questions. Yes, and these are the previous year's questions. So up to this point we have been discussed, and now let's see the remaining things. Okay, fine now. So now let's discuss about location of most or critical slip surface. Location of critical slip surface by Fellenius. He is a Swedish scientist. So he's a Swedish engineer. See, the Swedish circle method is there, right? So once the Swedish circle method is going to be completed, now there comes one more Swedish scientist, Fellenius. He has given location of critical slip surface. Now, so what is this location of the critical slip surface? Look, as I told you, the last topic in the previous session, all the methods are trial and error methods. Yes, which means we take different trial slip surfaces, we find out the factor of safeties, and then we say whichever has a minimum factor of safety, that is going to be critical slip surface. Now, the Fellenius has approached a method, and through this method, you can directly find out the critical slip surface. Now, let's see how. Yes. So if this is a slope, and the slope angle is going to be I, and let's say the height of the slope, whatever the height of the slope, this as h. H means height of the slope. So height of the slope. Now, if this is the conditions, you know the soil has a property C phi gamma. Apart from that, this Fellenius has taken for any slope you take, whatever this is nothing but I, you know that I means slope angle. Slope angle. Based upon the slope angle and based upon the height, the Fellenius has drawn a line known as Fellenius line. The Fellenius has drawn a line known as a Fellenius line. How, sir? Now, based on the I means slope angle, so based on I, this I value, 20 degrees, 30 degrees, 40 degrees, something like that. There are two other angles known as alpha comma beta. Based upon the I value, there are two angles known as alpha comma beta, where alpha comma beta are known as directional angles. Directional angles. Mind it, these angles are not the fixed values. They depends upon the slope angle I value. So if you see the slope, based upon the slope I, you are going to take two other angles alpha comma beta. Now, from the toe, based upon this alpha comma beta, we are going to draw two lines. We are going to draw two lines. One is with respect to the slope face. See, from the toe, with respect to the slope face, we are going to draw a line making an angle. We are going to draw a line and this should make an angle alpha. So what is alpha? Alpha is angle made by a line passing through the toe with respect to the slope face. Similarly, we are going to draw one more line with respect to the top of the slope. With respect to the top of the slope. Now I am going to draw one more line with respect to the top of slope. Mind it, this is going to be make an angle of beta with respect to the horizontal. So for a given slope, wherever you take, whether it's an embankment or earth dam or canal cut, it must be having a slope I. And based upon that slope angle, there is a one table which represents for different values of I, what is the alpha comma beta given by the Fellenius. And based upon that, I'm going to draw two lines, alpha comma beta, and these two lines. Now, I'll extend these two lines in such a way I'll be extending these lines. So if I do extend, now these lines are going to be definitely meet at some point. And now, whatever the point, let's say this point as a P. Let's say that point as P. So, and then what we do? So below the below the toe at a height h, again yes, below the toe at a height h, and at a distance of 4.5 times of h. So look, this is a h and this is going to be 4.5 times of h. So now again from the 2 point. So this Frobenius has given this is h and it is going to be 4.5 h. Now make sure this is the point. So make sure this is the point. See, this is point P and this is the point at which locates at what depth? H below the toe and horizontal distance of 4.5 h. So now we draw a line by joining these. So whatever this line is known as a Frobenius line. And now let's extend this line further. Yes. So now this is known as a Frobenius line. This is known as Frobenius line. Location of critical slip surface. So whatever this line is known as a Frobenius line. So how you have drawn the Frobenius line, sir? At first I draw two lines by making an angle alpha comma beta, where alpha comma beta represents the direction angles, and then I made a point of h and 4.5 h from the toe. So by joining these points, we are going to draw the line known as Frobenius line. So then what is the importance of this Frobenius line, sir? Sir, now you see, sir, on this Frobenius line, you see whatever this represents the critical slip surface trial ones. These are the centers. Whatever the points represents the centers of the critical slip surfaces. So 1, 2, 3. What are those? Are centers of trial slip surface. Sir, now what to do, sir? Sir, yesterday I have said you, for example, if I take one center, okay. If I take one center, for example, see, yes. From the Frobenius method, I am saying I'll be taking one point, one center, one. So this is the center point, which is going to be 1. Let me take this as a 1. So this is the center 1 I have taken. These are the center 1. Now what I do is I'll just simply draw a circle by taking this as radius. So whatever, this is nothing but passes through the toe. So now this is a radius. You know that this is the radius because just now I took this as a center, right? Now draw the slip surface. Draw the slip surface, and once you draw the slip surface, then you can join these also. So now this is also going to be R, and this is the theta that you can find out, because if you know the center, can't you find out the theta value? Yes or no? You're just drawing an arc, right? Now you use the Swedish circle method to determine the factor of safety. Once you determine the factor of safety, see, this is for slip surface, means for center 1. Similarly for center 2. Similarly for center 3. You are going to determine the factor of safeties. Now what you do is, whatever the factor of safety that comes now, for example, with the center 1, I got a factor of safety as a 2. I'll plot the factor of safety as a 2. F1 is equals to 2 like this. And now for center 2, I got factor of safety as a 1.5. And for center 3, I got factor of safety of 3. So now whatever you see, what I am representing is, for this center, if I take 1 as a center and if I draw the slip surface and if I find out the factor of safety, I got it as 2. For this center 1.5, for this center 3. And now you please join on this. If I join this, location of critical slip surface. Okay. So if I join this, see, for this center 1, factor of safety is 2. For this center 2, factor of safety 1.5, somewhere over here. Now if you observe, wherever you see the minimum, right, and this is going to be the factor of safety, minimum factor of safety, minimum factor of safety, and this is the critical center for the minimum, critical center or center for the critical slip surface. So felonious line provides center for critical slip surface. What we do is, you take some trial centers and you find out the factor of safety. If you plot those, after plotting a graph, you can see the minimum point should be there or not. At that minimum point is known as a F minimum. And now you see whatever this point B represents. Point P represents center for critical slip surface in clays. See, in the case of clays now, directly it represents the point P, means the point where the direction angles are going to be coincide. So this is the location of critical slip surface. Mind it, this location does not depends upon the soil properties. It depends upon whom? Slope angle I. Have a look. There are a lot of people trying to log into this site, but it's not opening, my friends. Contacting me, sir, to inform you. See, I hope you people got to know that that June has to be updated by 30th of last month, means by day before yesterday. It should be updated. If you are having any problems in login, please update the Zoom app. Whatever the Zoom app you are using, please update that Zoom app. Then I don't think you will be having a problem. So how to get factor of safety in this? Yes, you see, you use any method. For this one, you use by phi u is equals to 0 analysis. If you want to go for phi u is equals to 0 analysis, then you got the factor of safety Cu into L bar into R by W into X. By Swedish circle method, what is the factor of safety? C into L bar plus sigma n into tan phi by sigma t. See, the procedure is same as earlier. Once you know this factor of safety, for trial 1, the factor of safety, trial 2, F2, trial 3, F3. So once I know the factor of safeties, then I plot those the factor of safeties. I got F12, F2 as 1.5, and whichever is minimum, that is a minimum factor of safety. And this point is the center for the critical slip surface. Okay. Now, let's see the next condition. Next one. Friction circle method. Friction circle method. See how to find out means this. What is the purpose of this friction circle method? The purpose of the friction circle method is, see, we are not going to discuss full length of the friction circle method over here. I'm telling you again, I'm not going to discuss about the full length of the friction circle method. What I do is, what is the application of the friction circle method to the Taylor stability chart? See, I told you different methods are there for determining the factor of safeties in the case of finite slopes. I told you about phi u is equal to 0 degrees analysis, Swedish circle method, Bishop's method, friction circle method, and then last one is a Taylor's stability chart. So my dear students, Bishop's method is not required for you, and friction circle method is discussed or will be discussed for the sake of Taylor stability chart. What I want to say here is, out of all the chapters, this is the most theoretical chapter. Why I say is, and moreover, whatever the methods we are using now, this friction circle method and all those things, these are not the methods that we are using now in reality. These are outdated methods. But for undergraduation, for UG level, these are the methods. But if you go to post-graduation, there are different slope stability analysis. So Morgenstern price method, Jambu's method, there are a lot of empirical methods are there, and we don't do the analysis manually. We have a software, GeoStudio. It's a software to analyze stability of slopes. So if you go to the MTech, in the MTech, in order to study the safety of a slope, you have a software known as GeoStudio. And in that GeoStudio, you just draw the slope, it will analyze and it will give you the factor of safety, critical factor of safety. But as we have the syllabus for the gauge, and I'm telling you, these are going to be the most tedious and a typical process. And all the methods are trial and error methods, I told you clearly. So how many times you will do the trials, sir? 3, 5. If you take more number of trials, then you get more appropriate factor of safety. So the minimum trials are 3 to 5 trials. So this is the GeoStudio, means this is a software that we use. Even while I was doing my MTech in IIT Hyderabad also, I have done my project in stability of landfills. My project is stability of landfills. I hope you know the municipal solid waste landfills would be there, right? So means stability, means I studied about all these factor of safeties only. But I'm telling you, none of these methods are going to be useful in reality. In reality, for stabilizing the slope, we are going to use the software known as GeoStudio. There are some other softwares. Plaque and Plaxis. See, these are the softwares that we are going to use. Plaque This is based upon the finite element method. FEM, I hope you know that. FEM, right? Finite element method and finite difference method. So based upon these methods, we have two more softwares known as a FLAC and a Plaxis and GeoStudio. So these are the softwares we use in general to analyze a particular slope. So my dear students, do not worry about too much into these methods. I'm telling you, do not worry too much into these methods. So you need to know just what is what, how to determine the factor of safety. And for the friction circle method, I'm not going to discuss about the factor of safety also. So what is a friction circle method and how it is going to be useful for us in the next Taylor stability standard. So in the case of friction circle method, what we do? Again, okay, this is a slope. Take a trial slip surface. This is a slip surface. And for this trial slip surface, definitely there must be a center, right? Center O. From the center O, this is the radius R. This is the radius R. So for this soil, there must be some property C, phi, gamma, and there is some slope angle known as I. So in the case of friction circle method, the major thing that you need to know here is friction is assumed as fully mobilized. So what is the meaning of friction is assumed as fully mobilized, sir? Yesterday or day before yesterday, if you remember, I have given you some factor of safeties with respect to friction, with respect to cohesion, and with respect to shear strength. I hope if you remember, with respect to friction means F phi tan phi by tan phi m. Remember, if it is a fully mobilized means whatever the friction that mobilized is equals to the actual angle of internal friction. So phi m, the mobilized phi value should be taken as phi. Now, by taking this phi value, so we are going to take or we are going to draw one more circle with respect to the same center known as concentric circle. We draw a concentric circle. We draw a concentric circle like this, and mind it, and this circle is known as friction circle, and whatever the radius of the circle is there or not, the radius of this circle is known as r sin phi m, r sin phi. Look, my dear students, this method is suitable for cohesionless soils and cohesive soils. And if you make phi is going to be 0, which means for cohesive soils, if phi 0, in the case of the pure clay, when phi is equals to 0, then what is the radius here? 0. Then the friction circle is going to be a point. So here the friction circle is entirely dependent upon whom? Phi value. That is the reason why the friction circle is known as friction is assumed as a fully mobilized. So in this method, the revolving is depends upon the phi value of the soil mass. Sir, then what is its significance, sir? Sir, you see, This is a soil wedge. This is soil wedge. My dear, if you look over this figure, see, once the soil is going to be sliding, this portion is going to be separated from the rest of the soil mass or not? Once the soil is going to be sliding, whatever the sliding portion is going to be, rest means this is going to be move away from the rest of the soil mass through the slip surface. Yes or no? Then between these two soils, this is a soil and this is a soil. Between these two soils, there must be a reaction. Yes or no? That is known as a resultant reaction. So now, whatever the resultant reaction between these two soil masses, that is divided by the slip surface, that reaction, let's take it as R dash. Let me take R dash as resultant reaction between the soil masses divided by slip surface. Resultant reaction between the soil masses divided by slip surfaces. And if there is a cohesion force acting along the base, C is a cohesion force acting along slip surface. C, this is known as capital C, and this capital C is nothing but whatever the mobilized cohesion into length of R. Because see, I am asking you whom? I am asking cohesion force. What is meant by cohesion force? Cohesion force means cohesion intercept into area. So what is the area over here? The area is nothing but the area of R. And now, if W is the weight of soil wedge, so now this is the weight of soil wedge. Now, what is the meaning of all these things, sir? Now, if I draw a tangent, from the friction circle, if you draw a tangent, now, whatever the tangent that drawn from the friction circle, this tangent represents the resultant reaction R dash. So now you tell me what is meant by here. The tangent drawn from friction circle, represents the direction of resultant force or reaction. So if you take the force polygon, if I take the force polygon, now you see the force polygon here. The force polygon is going to be, looks like this is the weight, and this is going to be cohesion force, and this is going to be the resultant reaction R dash. This is a force polygon, So my dear students, what I want to look over here is in this method. You don't go beyond this. You don't go beyond this. So what I want to look over here is what is the radius of friction circle r sin phi. And in the case of the friction circle method, what is the assumption? Friction is fully mobilized, so that phi m is equals to phi. And what is the resultant force? That is a reaction between the two soil masses. And how you are going to find out that? By taking the resultant reaction as the tangent from the friction circle represents the direction from the direction of the resultant. That's it. You don't go anything beyond this. I'm telling you, you don't need to worry about anything beyond this. Okay. Now, there comes the last method. The last method is Taylor's stability chart or method. Taylor's stability method or stability chart method. So this is a chart which produces the how to determine the factor of safeties. Mind you, this is a procedure. Now coming to the Taylor stability chart. Again, see, this is the last method and this is very important for the GATE examination. I'm telling you, this method is very important for the GATE examination. And this is just an algorithm. You know the meaning of algorithm, right? A procedure to determine the factor of safety. A procedure to determine the factor of safety. Now, again, let's take so again this is a slope. If h is the height of the slope and I is the slope angle, C comma phi comma gamma are the soil properties. C comma phi comma gamma are the soil properties. Taylor proposed a number known as stability number to find factor of safety. Taylor proposed a number as stability number represented with Sn. Stability number represented with Sn. So what is this stability number, sir? This stability number Sn is given as Cm by gamma into H. Cm by gamma into H. Okay. And now this is purely based on friction circle method. This method is based on, means the Taylor stability chart is based on friction circle method. What is the meaning of friction circle method? Friction is going to be fully mobilized. Yes. So now you know whatever the factor of safety is. If you remember earlier, factor of safety with respect to friction is tan phi by tan phi m. Factor of safety with respect to cohesion is C by Cm. If you have any doubt, you please go through the previous classroom notes, then you can get that. Now, my dear student, you see the stability number is given as Cm by gamma into H. Now, can I write this Cm as a C by Fc into gamma H? Can I write this Cm as a C by Fc into gamma H? If I do so, then the stability number is given as C by Fc into gamma into H. From this, Fc is equals to C by Sn into gamma into H. So this is the final equation that we used to determine the factor of safety with respect to whom? With respect to cohesion. With respect to cohesion. So based upon the stability number is going to be used to determine the factor of safety with respect to cohesion. And this method is going to be suitable for cohesive soils. If you say cohesion-less soils, C is going to be 0. Now, Fc is equals to C by Sn into gamma H. Fc is equal to Sn into gamma H. Now, sir, you are saying he has proposed his number Sn, but on what basis it is going to be depends on? Now, look, this Sn depends on slope angle I, comma phi m or I, comma df. What is meant by df, sir? Df means depth factor. You please go through the earlier values. You will get to know that depth factor. See, for I value means what is meant by I value? Slope. Yes, for I value slope. And what is meant by phi m? Phi m means mobilized friction. You know that. M means mobilized. And df for the corresponding I comma phi m or for the corresponding I comma df. Keep that in your mind. Either you can use I comma phi m or you can use I comma df. You can find out the stability number given by the Taylor's stability chart. Mind it, in the examination, they are going to be provide you the stability chart. Means for the corresponding I, like I give I 20 degrees, phi 15 degrees, I'll give you the Sn value. Or I'll show you that. So my dear students, if you look over here, you please observe this. What is this meaning? Stability number, right? So for the phi value and I value the Sn. For the phi value and I value the Sn. So the I depends upon the phi and I. So now, if you see, once we know the phi m, then we can find out the stability number. Now you can get a question. Are sir, we have C phi gamma. As we don't know Cm, then I can convert the Cm as a C by Fc. But now, as I told you, Sn depends upon I comma phi m. Do we have phi m or do we have phi? Do we know the mobilized friction or do we know the only phi value? We know only phi value. So now from this, what I do is, as you know, Fi is equals to tan phi by tan phi m. If f of phi is mentioned, if f of phi is mentioned, keep that in your mind. If f of phi is going to be mentioned, then tan phi m is equals to tan phi by f phi. So phi m is nothing but tan inverse of tan phi by f phi. Tan inverse of tan phi by f phi. Look, Sn depends upon whom? I comma phi m. I know the S value. Now I need to find out the phi m value. By using the f phi, if f of phi is mentioned, I can take f of phi is equals to tan phi by tan phi. Sir, what if they don't mention anything regarding to the, what if they don't mention anything regarding to the factor of safety with respect to cohesion, sir? Now you see, sir, this is a condition A. If Fi is not mentioned, assume friction is fully mobilized. Sir, what is the meaning of friction is going to be fully mobilized, sir? So just before this, if I say friction is going to be fully mobilized, then the actual meaning of this one is the factor of safety with respect to friction is going to be 1. Then phi m is equals to 5. Yes or no? See, if I keep Fi as 1, then tan phi becomes tan phi m. Then phi m is equals to 5. So, my dear students, if I want to find out the factor of safety with respect to cohesion, C by Sn into gamma H. We have C, we have gamma, we have H. Now our entire question is going to be regarding to the Sn. So, for finding the Sn depends upon I comma phi m. Okay, and if f of I is mentioned, by using Fi is equals to tan phi by tan phi m, you can find out the phi m. But if there is no Fi they mention, just assume friction is fully mobilized. That is the reason why we said this method is based upon the friction circle method. So then you can use this one. So you know the phi m is equals to phi value. You check the table for the I, for the phi m, what is the Sn value? Substitute over here to determine the factor of safety with respect to cohesion. Now, coming to the special conditions over here. A, canal full condition. You know that whenever the canal full condition comes into existence, gamma becomes gamma dash. And then what is the factor of safety, sir? C by Sn into gamma dash into H. C by Sn into gamma dash into H. Sir, why you took canal full condition gamma is equals to gamma dash? You please go through the yesterday's class. There you can understand why I have taken gamma as gamma dash. So factor of safety with respect to cohesion Fc is equals to C by Sn into gamma dash into H. Okay. Now, here you know that Sn depends upon I comma phi m. Next, last condition in this canal sudden drawdown condition. In the case of canal sudden drawdown condition, gamma is going to be used as gamma sat, and Fc is equals to C by Sn into gamma sat into H. C by Sn into gamma sat into H. See, this Cm means mobilized cohesion. Cm means mobilized cohesion. So you can write the Cm as a C by Fc. C by Fc. So that's the reason why C by Fc into gamma into H came. Now, this Sn here, this Sn depends on I comma phi W. This phi W means weighted friction angle. See, this canal sudden drawdown means a C-phase condition or not? Canal sudden drawdown means a C-phase condition. You know that whenever the C-phase condition comes into existence, the factor of safety is going to be decreases. So this phi W is given as gamma dash by gamma sat into phi m. Look, in the case of the canal sudden drawdown condition, see, these are not the things that we took. These are the things based upon the Taylor stability chart. I told you already, in this Taylor stability chart, it's just an algorithm. It's just an algorithm how to determine the factor of safety. In the case of canal full, you take gamma as gamma dash. In the case of canal sudden drawdown, you take gamma as gamma sat. But the Sn is depends upon I comma phi, where phi W, where phi W is known as weighted friction angle, and phi W is equals to gamma dash by gamma sat into phi m. So once we know the phi w, then you go for the back, whatever the value. See here the values are represent, right? Whatever the given values, those are reduced values only. Those are the reduced values only. So if fi is not mentioned, you take phi m is equals to phi. And once you know phi m, you can find out the phi w, gamma dash by gamma sat. So this is about the procedure in Taylor stability chart. Please have a look once again. Okay. With this, we have completed the chapter. Now let's see the questions. See, let's see the questions. Classroom practice questions. Question number 4, because we have been discussed about the 1, 2, 3 DP for yesterday. We discussed about this 1, 2, 3. So now let's go with the question number 4. This is also a classroom practice question. A cutting is to be made in a soil deposit with a slope of 25 degrees to the horizontal, which means I is going to be 25 degrees for a depth of means 25 meters. What is the meaning of cutting, sir? Canal cut, sir. So you are going to do a canal cut like this. This is a canal cut, and it is mentioned that it is going to be done 25 meters. And what is the slope over here? The slope is going to be 25 degrees. And it has a some C value, phi value, gamma. C 35 kilopascals, phi 15 degrees, gamma 20 kilonewton per meter cube. So now question number E, you see. Sir, find the factor of safety with respect to cohesion. A, I am asking you factor of safety with respect to cohesion. If the factor of safety desired with respect to friction is going to be 1.5. Keep that in your mind. Now, for factor of safety with respect to cohesion 1.5, what is the factor of safety with respect to cohesion, sir? You please observe this table. This table represents the stability number or not? When they give the stability number, what is the meaning? It's a stability chart, right? Yes or no? Yes. So, my dear students, now how to approach this problem? Everybody have a look. So, everybody have a look. You observe, first of all, isn't a canal full or canal sudden drawdown? No. Number 2, what is the factor of safety with respect to cohesion? C by Sn into gamma into H. Okay, I have C, yes. I have gamma, yes. I have H, yes. So everything is there. Now only Sn. Accept or not? Okay. And I told you Sn depends upon I comma phi m, means mobilized friction angle. Now for that what I said, if Fi is mentioned, you find out phi m. And if Fi is not mentioned, you take phi m as a phi. But now they're asking, I want a desired of f of phi, how much? 1.5. So I will use Fi as tan phi by tan phi m. So now, what is phi m, sir? Tan inverse of tan phi by Fi. Tan inverse of, what is the friction angle I have given? 15 degrees by, what is Fi they have mentioned? 1.5. Please let me know the value. So this is going to be 10.13 degrees. So now you see, let's go to the table. Let's go to the table. Everybody have a look, please. Listen. Now I gave some values of 5 values. See, the meaning of this 5 values, mobilized values only. Whatever this represents, these values are represents, sir. They give 5, 15, sir. So I have 15, sir. Can I take directly Sn, sir? No, sir. You have to take the mobilized value, sir. So now, what is the mobilized value, sir? 10.13. So if you look, they have given 15, 10, and 12.5. And what is the nearest value, sir? The nearest I can take it as 10 degrees. So from data, whatever the I, 25 degrees, and whatever the phi m, 10 degrees, you see for this, what is the stability number? Phi 10 degrees, I 25 degrees. What is the stability number I have? 0.06. So my dear student, first of all, you reduce the phi to phi m and you find out the phi m value for the given whatever the 10 degrees for that friction angle 10 degrees. What is Sn? 0.06. So Sn is given as 0.06. So now you please substitute. Fc is equals to C by Sn into gamma H. What is the C value? 35. What is Sn? 0.06 into what is gamma? 20 into 25. So tell me the factor of safety with respect to cohesion. So it is going to be 1.167. This is going to be 1.167. So, sir, what about in the case of the IES? Please listen. In the case of the IES, they will give you the stability number directly. They will mention you the stability number directly. And one more point I want to say over here. Look, in case phi is equals to 0 degrees and I can be 90 degrees, then the stability number is going to be maximum of 0.261. Stability number is going to be maximum of 0.261. Actually, there is a table, Nana, and according to the table, for phi 0 degrees, you see this phi 0 degrees, sorry, I 90 degrees and phi 0 degrees, the stability number is maximum, then that is going to be 0.261. Why? Wait for that, I'll be showing you. So now I hope you understood how to determine the factor of safety with respect to cohesion. Now, let's see what is the next question. Instead, if factor of safety with respect to cohesion is going to be 1.5, what would be the factor of safety with respect to friction? So this time they gave a factor of safety with respect to cohesion as 1.5. Then what should be the factor of safety with respect to friction? So now again, now this time reverse the procedure. Fc is equals to C by Sn into gamma into H. Now I know Fc. What is C value? 35 by Fc 1.5 into 20 into 25. So 35 by 1.5 into 20 into 25. So what is this Sn value? 0.0467. So this is the Sn value I got. Now from data for I 25 degrees, when Sn is going to be 0.0467, now the nearest value of Sn 0.0467 is 0.05. The nearest value of 0.047 is going to be nearest of 0.05. 0.05. Now you see, for the Sn 0.05, I value 25. What is the phi m value I am going to get? 12.5 degrees. So phi m is equals to 12.5 degrees. See, just I am repeating the procedure. At first here I find out phi m from their Sn, from their Fc. But now here I know Fc from their Sn. From Sc I am finding Sn. From Sn I am finding the phi m. Then what is Fy, sir? Tan phi by tan m. Tan 15 degrees by tan 12.5 degrees. So please tell me the Fy value. See, can't we interpolate, sir? Sir, the variation is going to be very less, sir. That's the reason why I'm not using any interpolation. The variation is going to be, see, 10.13 and 10, both are almost same. If it would have been 11 or 11.5, then I can take the interpolation. But the values is very, very small level, right? Or small range. So you don't need to worry about the interpolation. What is the factor of safety here? .208. If they ask two decimals, 1.21. That's it. So this is the factor of safety with respect to cohesion and with respect to friction, based on whom? Friction angle. So, but they given phi as 12.5. How phi m you have taken, sir? Nana, phi m means mobilized friction. Okay, they have given phi 15 degrees. Now, once I got, then I got phi m means this value, whatever this values, this represents the mobilized friction only. Those are representation of phi m only, but they give as phi. So, once you find out the phi m, whatever the phi m, you just look over there. For that corresponding friction angle. See, what is mean by phi m? That is also friction angle. Phi is also friction angle. Phi w is also friction angle. Now, I hope you understood this. Have a look once. Okay. See the next question. Now this question is also going to be based on the Taylor stability only. Now a new canal is excavated at a depth of 5 meters. So canal is going to be excavated at a depth of 5 meters. And what is the C value? 1.4 ton per meter square. Phi value 15 degrees. Gamma sat as 1.945 ton per meter cube. And slope of the bank is 1 in 1. One vertical to one horizontal. Calculate the factor of safety with respect to cohesion. So what I am asking you is FC. When canal runs full, and if it suddenly emptied also, what will be the factor of safety? You know that, FC is going to be C by Sn into gamma H. Yes. At first, I explained all these things. Now, let's come to the canal full condition and canal sudden drawdown condition. A. Canal full condition. Sir, in the case of the canal full condition, Sn depends upon I comma phi m and gamma is equals to gamma dash. So my dear student, now observe the question carefully. Have I mentioned any f of I in this question, please? Have I mentioned any f of I in this question? Have a look. Means factor of safety with respect to friction. Have I mentioned anything? But you see this question, I mentioned the factor of safety with respect to friction as 1.5. But in this question, have I mentioned anything regarding to Fi? No. If I don't mention anything regarding to Fi, if F of I is not mentioned, assume friction is going to be fully mobilized. Assume friction is going to be fully mobilized. So now you see, if I say the friction is going to be fully mobilized, assume, or you can write as F of I is not given, assume friction is fully mobilized. If friction is going to be fully mobilized, then phi m is equals to what is the value? 15 degrees. 15 degrees. So now from data for phi m is equals to 15 degrees, what is the Sn value? 0.083. 0.083. Now what is the factor of safety, sir? Fc is equals to C value, sir. C by Sn into gamma dash into H. What is C value? 1.4 by 0.083 into what is gamma dash? 1.945 minus 1 into what is the H value? The H value I have given as 5. So find out the factor of safety, please. (0.083 into 1.945 minus 1 into 5. What is the factor of safety, please? See, you know that, I told you these conditions. In the case of canal full condition, you have to use gamma as gamma dash. So after solving, (3.57). The value is going to be 3.57. Okay. So now similarly, you please find out what happens. B. Canal sudden drawdown. In the case of canal sudden drawdown, You use gamma as gamma sat and Sn depends upon I comma phi w. So what is phi w, sir? Gamma dash by gamma sat into phi m. Gamma dash by gamma sat into phi m. Already you know what is meant by phi m. Yes. Now phi w is equals to gamma dash 1.945 minus 1 by 1.945 into phi m as 15 degrees. 1.945 minus 1 by 1.945 into 15. This is going to be 7.287 degrees, which means I can take it as 7.3 degrees. Okay. So now I find out the phi w. I told you in the case of canal sudden drawdown condition, you have to take a weighted average, means weighted friction angle. Now I can give you logic. After all solving this, I don't want to solve all this procedure. I don't want to waste my time. Can I say, go back, phi w is almost half of phi m. Why, sir? Because gamma dash is almost half of gamma sat or not? Yes or no? Now, phi w is almost half of a phi m. You see, what is the phi m value? Here, phi m is equals to, phi is equals to how much? 15 degrees. But what I got is 7.3 degrees or not? Yes or no? See, in the examination, my dear students, in examination, I am telling you again clearly, in examination, if they mention canal sudden drawdown, you directly take half of the friction angle. Because this 7.3, we are going to approximate it to 7.5 degrees. Now you go back to the data. You see that data? Now for 7.5 degrees, what is SN value? 0.122. So from data, what is SN value? SN value is going to be 0.122. 0.122. So now what is FC? C by Sn into gamma sat into H. What is C value? 1.4 by 0.122 into gamma sat 1.945 into 5. Can you please tell me what is the factor of safety with respect to cohesion? 1.18. 1.18. So please have a look how I am finding for canal full condition. See, these two problems I discussed, this covers entire models of the stability number methods. First I am finding the phi w. See, focus on the procedure. You know FC, but what you require? Sn. Sn depends upon I comma phi m. Canal sudden drawdown phi w. What is phi w? Half of phi m. I hope you have done this now. Now you see the question number, this is question number 5, and now coming to the question number 6. Question number 6. An embankment is made with a cohesive soil. An embankment is made with a cohesive soil with a shear strength parameters as C dash and phi dash 15 degrees, which means it has some portion of the sand also or silt also. C dash is 30, phi dash is going to be 15 degrees, 30 kilopascals, phi dash 15 degrees. The average effective stress on the plane is going to be 100 kilopascals. Average effective normal stress is going to be 100 kilopascals. Find the extreme values of Fc and Fi for a mobilized shear strength of 39.25 kilopascals. First of all, what is the meaning of extreme values of Fc and Fi? See, for extreme value of extreme factor of safety of one parameter, other parameter should be fully mobilized. Other parameter should be fully mobilized. Sir, what is the meaning of this one, sir? Have a look. For extreme factor of safety of the one parameter, for example, for extreme factor of safety of one parameter, Fc, for extreme Fc, what is the other parameter? Friction. What is the meaning of friction is going to be fully mobilized? For extreme parameter of Fc, then F5, F5m is going to be 5, then F5 is equals to 1. So, for extreme Fc, the other parameter should be fully mobilized so that the friction means factor of safety with respect to friction is going to be 1. Similarly, for extreme F5, Fc should be equals to 1. So mind it, my dear students, this is a new point that you are seeing here. For extreme factor of safeties of one parameter, other parameters should be fully mobilized. Now, does this mobilization concept comes into the existence or not? Here I am not going to use any stability number or friction circle method or something else. This is just based upon the mobilization techniques. Yes, you know that from the mobilization techniques. From the mobilization techniques, you know that factor of safety with respect to shear strength is nothing but S by Sm, which is going to be C plus sigma into tan phi by Cm plus sigma into tan phi m, and factor of safety with respect to cohesion as C by Cm, factor of safety with respect to friction as tan phi by tan phi m. So these are the factor of safeties. Now let's see how I am going to find out this one. Let's see. Come on, listen over here. What is Sm? What is Sm? Sm is equals to Cm plus sigma into tan phi m. Okay. Sm is equals to Cm plus sigma into tan phi. That's it. Means mobilized shear strength. Mobilized shear strength. Now, can I write this Sm is equals to, you see, can I write this Cm as a C by Fc? I can write this Cm as C by Fc. C by Fc plus sigma into tan phi m as tan phi by F phi. If you have any doubt, you please look over here. What is tan phi? Tan phi m is equals to tan phi by F phi. Okay. Now, that's it. But the given values are drained or undrained? Drained. So now I can write this one as Sm is equals to C dash by Fc plus sigma dash into tan phi dash by f phi. My dear students, I have SM with me, C dash, phi dash, and sigma dash. SM with me, C dash, phi dash, and sigma dash. What are the only unknowns? FC and FFI. So now there comes. For extreme FC, F5 should be is equals to 1. Yes or no? So now please substitute the values over here. Whatever the given SM 39.25 is equals to C dash. What is C dash? 30 by FC plus what is sigma dash? 100 into tan phi dash 15 degrees by Fi as 1. So now you please solve it and let me know the FC value. Similarly, for extreme Fi, FC is equals to 1. Then 39.25 is equals to 30 by this time FC is equals to 1 plus 100 into tan 15 degrees by F5. So find out the Fi and the FC values. So why this is happening, sir? What is happening, sir? Why you are worrying that much, sir? Huh? What's there in all these things, sir? What's there in all these things, sir? For everything, there must be some ground rules, sir. Those are the ground rules, sir. You need to look over. Mr. Harshvardhan, what is the complex over here? Tell me. What is the complexity over here? Is there any complex over here? I have given you the exact procedures. Yes. I have given you the exact procedures. So what is the stability chart? And what happens if Fi is there? What happens if Fi is not mentioned? What happens if it is a canal full condition? What happens if it is a canal sudden drawdown condition? And I have solved the questions also based upon that. 2 questions I solved and I explained both the ways. Then where is the complexity? Where is the complexity? I don't get. I have given all these things, right? They are saying fact if FC, Fi and mobilized shear strength, then you have to use these relations, right? Meanwhile, sir, when is the new chapter, sir? After this, I know this is going to be quite a boring chapter, and I feel the same also for the chapter number 15. But don't worry, after this, we are going to start chapter number 16, foundations. That's, yeah. So there is that next chapters are going to be beautiful chapters, and we are about to end the subject because once we start the foundations, so shallow foundations it take 2 days and deep foundations it take 2 days, and soil exploration and pile foundations in 1 day. So probably in the next 5 days we are going to complete the syllabus. Today is June 1st, so probably by June 6th or 7th, by June 6th we will be completing the subject. For the GATE and for IES, there is 2 more chapters extra, and for those 2 more chapters we'll be having 1 day for IES. That is exclusive for IES, not for GATE. And we'll take 1 day as a doubt clearing session, 1 full session as a doubt clearing session after that. So I think so June 8th onwards, so you'll be having the next subject. From June 8th onwards, you'll be having a next subject. So the next subject will be from the June 8th probably, and I hope so will be finished by June 7th. So it's too, I know it's going to be, it's really too hectic to see one person for such a long time. So you people are seeing me from the past 31 days, I think so. This is the 31st or 32nd day. And you have to bear me for the next 4 or 5 days. So even I did not spend this much amount of time for one single batch for a single subject. I used to spend generally 10 to 14 days in the normal offline classes, but this is too much of time. So bear with me, I hope. Sir, how come we contact you for doubts for geotech? You can contact me. You have my mail ID and you have official ACE Civil Telegram channel is there. So you can contact me through that. You can, if you mail me, I'll try to reply as soon as possible. If I means I may not give you immediately, but I can give you. After exam, you give the replies. Yes, right. I mean, the person who has given a reply after examinations, sir, will you give the reply after the examinations? Yes, I will give you the reply for after the examinations because after examination, you are going to tell me what's your rank, then I'll give you a reply also. Okay, fine. What is the FC and FI values? Please let me know. The FC 2.4 and FI has 2.89. 2.89. That's it. Okay, now see, Telegram channel is not found. I told you whatever the Telegram channel I kept you and I said you it's not working. So that's the reason why I deleted. And you please go through the ACE Civil. ACE Civil. If you type it, you can get it. Now let's see the next. So some of the previous ESE questions and GATE questions. I have already solved a few. So with this, we'll conclude the chapter. Some questions are there. In a clay soil, my dear students, please look. In a clay soil having gamma 50 kilonewton per meter square as unit cohesion and 18 as unit weight. So an excavation is made with a vertical face. What is the meaning of excavation made with a vertical face? What is the meaning of excavation made with a vertical face? I is equals to 90 degrees. And you see the clay soil mass phi is equals to 0 degrees. What is the stability number they have given? 0.261. I told you, my dear students, in the case of clay, only there is a vertical cut. And that cut is going to be maximum up to critical height HC. So they have given the stability number 0.261. What is the maximum depth of excavation so that vertical face remain stable? Maximum depth up to which vertical face remains same, remain stable, is nothing but critical height, and the factor of safety is going to be critical factor of safety, which is going to be 1. You know that simply maximum height means what is the factor of safety that you are going to provide? 1. Because if you go beyond that, factor of safety is going to be less than 1. Yes or no? Factor of safety, you please look. What is meant by factor of safety according to stability number? C by Sn into gamma into H. My dear student, clearly observe this factor of safety depends upon H. Yes or no? If H increases, factor of safety is going to be decreases. And if the maximum height, it is going to be stable, means if H is going to be increases, then this is going to be HC, then this is going to be FC. And if height is more than the HC, factor of safety is less than FC. So from the equation, F is equals to C by Sn into gamma into H. If I write H as a HC, F becomes FC. So, okay, this FC is equals to 1. So then, what is HC, sir? C, what is C value I have given? 50 by Sn, 0.261 into gamma value as 18. So please find out the value. Please find out the value and let me know. 10.6. So the answer is going to be 10.64 meters. So the nearest answer is going to be C. Now you see, for the stability analysis of the slopes of a purely cohesive soil, for the stability analysis of a slopes of a purely cohesive soil means sea soil, the critical center is taken as line, is taken to lie at an intersection of, you please go through this. My dear students, this is the location of critical slip surface or not? Yes. See, you see the critical slip surface for clays are going to be taken the lines intersection with an angles of whom? Alpha comma beta. Exactly this point P, whatever the point P I am representing over here, that represents the center for critical slip surface in the case of clays. No. So you see the critical center, if this is our slope, for the case of clays, whatever this is nothing but the point P, this is for clays, center for clays, and whatever these angles are nothing but alpha comma beta, and alpha comma beta are nothing but whom? Directional angles. So my dear students, the critical center is taken to lie at the intersection of the directional angles. So answer is going to be D. Answer is going to be D. See, these are the previous year's 2018 bits. That's the reason why I took. See, what's there in it? Maximum depth means the factor of safety is maximum, minimum. If you say that is a critical condition, so factor of safety should be taken as 1. Okay, fine. Yeah. Now, consider the following assumptions for slope stability analysis. The assumptions necessary for the friction circle method of analysis. You see, what are the assumptions necessary for the friction circle method of analysis? You please observe here. So I have given you these statements, and in this, based on the friction circle method, what are the assumptions? I told you friction circle method means friction is fully mobilized. Yes. Now, that is going to be a total stress analysis or effective stress analysis. So here you are going to take the total stress analysis. It's not an effective stress analysis. Resultant R will passes through the center of circle. You please observe. This friction circle method is there, right? So here you are going to take it as this is a total stress analysis, Nana. Friction circle method is a total stress analysis, not the effective stress analysis. This is a total stress analysis. That's the assumption. And now you see the resultant is going to be passing through the center or tangent to the friction circle. Tangent to the friction circle. Yes. So the assumptions near for the friction circle method of analysis would include resultant passes through center. No. Resultant is going to be tangential to the friction circle. So the correct one are 1, 3, 5. The answer is going to be B. So resultants, that's just assumptions. And now consider the following statements associated with the stability of slope. Stability number is inversely proportional to cohesion and directly proportional to height. Sn is nothing but C by Fc into gamma h. So from this I can say Sn is directly proportional to h. So here means directly proportional to C. Here inversely proportional to C. So this is wrong. Yes or no? Swedish method of analysis is based on circular failure surfaces. Yes. The failure surface is going to be circle. See, by seeing the first option itself, I can go for the answers. Can't you go for the answer first? As you see, the answer, the statement number 1 is going to be wrong. Then I can eliminate B, I can eliminate D, I can eliminate C. The answer is going to be 2 and 3 only. But now you check. Swedish method of analysis is based on circular failure surfaces. Yes. The Kalman's method. You please look over the previous chapter. Kalman's and Reban. Kalman and Reban are based upon the Coulomb's method. I hope you remember the Coulomb's method. In the previous chapter, Kalman's and Reban's are graphical approaches based upon the Coulomb's. And you know, according to Coulomb, the failure plane is going to be planar. Rupture means failure. So this is going to be true. The answers are going to be answer A. By knowing the statement number 1 itself, you can say the answer directly. Now, the wall shown in the figure, see, I have done these questions yesterday also, but this question I want to say, the wall shown in the figure has failed. The cause of failure, error made in the design of failed wall. You see, this is a wall. Think about clearly. This is a wall that's shown in the figure. The cause of the failure. What is the cause of the failure? Okay. You see, observe. What is this? This is a film soil. See the options. Deep slip surface failure. What is the meaning of deep slip surface, sir? The meaning of deep slip surface is going to be base failure. Base failure is known as a deep slip surface failure. Whatever the base failure is known as deep slip surface failure. But you see here, what is a soil? Film soil means hard soil. Hard soil. So as hard soil is located, so no base failure, which means the wall will not fail by means of a base failure. Number 1, A is wrong. Now you please keep the B aside. No proper drainage in the clay backfill. See, what is the weep holes or weep coil or hole? This is for drainage only, right? This is for the drainage. So weep holes provides drainage. So now this is also going to be wrong. So I'm just looking over the conditions. At first, deep slip means base failure. So as hard soil is located, no base failure. And no proper drainage. Weep holes are there, so you don't need to worry about the drainage. Now translation failure. I remember translation failure occurs in what type of soils, right? Translation failure occurs in the case of infinite slopes. But what is this? This is a finite slope, right? As it's a finite slope, it is not going to be happen. So the failure that you can see in the given wall is going to be overturning failure. How does overturning is going to be seen, sir? This is the overturning that you are going to see. So the wall may get overturned. Overturning failure. You don't need to find out the values. You just look over the options. You have to apply your concepts. When you apply, then you can understand the answer is going to be a overturning failure. What about compound failure? Compound failure, we don't need to discuss about Nana for the analysis. Does my audio is not audible to you? Does my voice is audible to you people? Now, there is a gate question. This is a previous gate question. So I have solved some gate questions yesterday also, means the day before yesterday. And this one is one of the question I solved. This is one of the question I solved. You please go through the notes. I have solved some questions. Now, the critical slip surface for a slope is shown figure. This is the critical slip surface, Nana. And mind it, what is it? Rotation. So which means finite slope. This is a finite slope. Length of arc L bar is given as 15.6 meters. And the area of the soil wedge is given as 82 meter square. 82 meter square. Radius of the slip surface R is going to be 10.3 meters. And what is the factor of safety? See, I don't want to remember the formula. I don't remember the formula. Even after these many years also, I don't remember the formulas. So now you see, they have given the weight and this is going to be X. So, right, factor of safety is nothing but resisting moment by driving moment. Resisting moment by driving moment. What is resisting moment? Resisting force into perpendicular distance by weight into perpendicular distance. Which means they have given weight, right? Okay. Now, what is the resisting force, sir? Resisting force means shear strength into length of arc into R by W into X. Sir, what is shear strength, sir? C plus sigma into tan phi, sir. And phi is going to be 0, sir. You see, phi u is equals to 0. So then this is going to be Cu into L bar into R by W into X. If you want to remember the formula, this is going to be phi is equals to 0 degrees analysis, right? Now, my dear student, I have Cu, I have L bar, I have R. Where is R? Yes, I have R. The numerator is with me. Coming to the denominator, I have X. Now coming to the weight. What is weight? Density of a soil into area of a soil into 1. That's it. What is the density of soil? Give me a minute, please. What is the density of soil over here? So 20 into area of soil given as 82 into 1. Can you please tell me this value? 20 into 82. So which is going to be 1640 kilonewton per meter. kilonewton only you just write it because the per meter is going to be this 1 meter. Okay. Now coming to the factor of safety. What is the factor of safety, please? 30 into L bar, 15.6 into R, 10.3 by 1640 into X as 2.3. What is the factor of safety, please? So 1.277. So you can take it as 1.28. The answer is going to be D. So these are the questions that we discussed about the sir. Why 50, sir? You please look over the questions. Sir, they mentioned sir 50. I hope you understood this. So with this, I have covered all the models. Look, let me discuss them. What are the models I have covered? Finite slopes. First, infinite slopes. I covered the models regarding to the infinite slopes. Coming to the finite slopes, I covered the model regarding to the phi u is equals to 0 degrees analysis and Swedish circle method. And I covered the model regarding to the Taylor stability chart. These are very, very important Taylor stability chart. So that's all about this chapter. So with this, I have completed the chapter number 15. Now we are going to enter into the chapter number 16. So that chapter is known as shallow foundations, or I'll be starting with as a foundations. I'll be starting as a foundations. So then I'll be discussing about what is shallow foundation and deep foundation. But further, we'll see break. Have a break. So now it's 11:03. Have a break up to 11:30. We'll start the new chapter at 11:30. Okay. Let's come to the next chapter, chapter number 16. So, come to the next chapter. I'll be starting this chapter as a foundations, and later on I am going to change. So first of all, what is meant by foundation? Everybody, what is meant by foundation? So chapter number 16, chapter number 15, not it's chapter number 16. So what is meant by foundation? Foundation is a lower part of any structure you take. Foundation is a lower part. What is this chapter 15 gonna? What is the meaning of a foundation? Foundation is a part of a structure. It's a part of a structure where the load, entire load from the structure is going to be transferred to the soil mass through the base. So let's take a foundation over here. Okay. So this is a foundation where, and whatever the representation, so whatever this is nothing but the ground level. So whatever the load coming from the structure, load, this is nothing but a column, right? And the foundation or a footing. Generally, footing refers to shallow foundation. Footing refers to shallow foundation. So this is a foundation is nothing but a foundation or footing. Actually, footing refers to shallow foundation, not for the deep foundation. I am representing you a shallow foundation. This is a shallow foundation. So now the foundation, it is a part of structure or lower part of structure that transfers the load, safely to the soil mass without any failure. So that's nothing but a foundation. It's a lower part of a structure that transfers the load safely to the soil without any failure. So now, what are the different type of foundations and what type of the foundations we are going to experience for different type of the soil masses? Look, basically there are two different type of foundations known as a shallow foundations and deep foundations. shallow foundations and deep foundations. So the foundations are going to be divided into shallow foundations and deep foundations. The biggest question here is what type of foundation we are going to take for where you want to take the shallow foundation and why you are going only for the shallow foundation at a particular depth. Mind it, you know that as is the lower part, our main aim is to allow the load safely to the soil without any failure. Okay. And we are going to send the load through the base. Yes or no? So through this base. And whatever, this is nothing but a soil mass. Look, if the soil mass is going to be dense or medium dense enough, which means if the soil has a good strength, you know that if the soil is going to be dense or medium dense, then its strength is going to be more. Yes or no? And when the strength is going to be more, obviously, then you can transfer the load at a shallow depth. So now let's take, this is a depth of foundation D and width of foundation as B, where D is depth of foundation and B width of foundation. So first of all, my dear students, as you know, sir, if depth of foundation is going to be less than or equals to 1, then we go for the shallow foundation. If depth of foundation to the width of foundation is greater than 1, then you go for the deep foundation. Generally, see, this is a nominal perspective, but my dear students, you need to know one thing here is the type of foundation depends upon two conditions. Number one, loading condition. Number two, type of soil. Repeating the point again, foundation depends upon two conditions. Number one, type of a soil, which is soil, on which soil you are going to construct. Number two, type of loading, and what type of loading you are going to construct. For example, if the soil is going to be medium dense, if the soil is going to be medium dense or dense, which means the soil has good strength at a lesser depth itself. Yes or no? Then you can go for the shallow foundations. So we go for the shallow foundations. If the soil is medium to dense, we go for the shallow foundations. Now, so when to go for the deep foundation, sir? When to go for the deep foundation? In the case of the deep foundations, means when we go here is, if the soil is going to be very weak and loose, then you have to go for deeper layers. Just think, Nana, initially if the soil is going to be loose, if you go deeper and deeper and deeper, the soil strength is going to be increases or not. So if the soil is medium to dense, strength of soil is more at lesser depth. So shallow foundation. If the soil is going to be loose and weak, then you have to go for the deeper foundations. And second one is, if the loading condition, or if the load coming from the structure is less, then you go for the shallow foundations. I'll ask you one question. I hope most of you people have seen a residential building construction. Residential building means where we live, or independent houses or villas. So what type of foundations we go for residential buildings? Shallow foundations. What type of foundations we go for the residential buildings? Shallow foundations. So shallow foundations are going to be used in the case of residential buildings. Why? Because the load coming from the structure is less. If load coming from structure is less. Example, residential buildings And if the loads coming from the structure is going to be very high, if the load from structure is large, then we go for the deep foundation. So if the soil is medium to dense, we go for shallow. If the soil is going to be loose and weak, we go for the deep foundation. Sir, now what is the advantages of the shallow foundation over the deep foundation, sir? This is going to be economical. This is going to be not economical or uneconomical. Uneconomical. Load transfers through base of footing only. Here, load transfers through sides and base. Loads transfers through sides and base. You see here in the case of the deep foundation, the example Burj Khalifa. I have already shown these figures earlier. So see, largest skyscrapers there, simply the foundation is going to be very deep foundation. Okay. So now let me give you an example for that. I'll explain both. You see, what I am representing here, this is nothing but a pile foundations, Nana. Whatever, this is nothing but ground level. Ground level, you please observe. Listen to me carefully. See, what is the meaning of this load transfers through the base of footing, sir? Whatever, this is nothing but a pile. This is nothing but a pile foundation. So what is the meaning of this pile? And why it is going to be uneconomical? Why the load transfers to solids and sides and the base? Everybody, if you observe, you see whatever the soil mass, when the load is going to be transferred, this load is going to be assumed to transfer through the base of footing only. Yes or no? Yes or no? And whatever the soil mass, see, this is also going to be soil, right? The load can be transferred to the sides also. Yes, but you see, in the case of the shallow foundations, we take the load transfer through base only. When you take the load transfer from the base, the side soil mass is not going to be contribute anything. The side soil mass is not going to be contribute anything. So, my dear students, here, when you apply the load, whatever the soil mass beneath over here, so B is width, whatever the soil mass beneath, this is the only thing that offers a resistance. This is the only thing that offers the resistance. In the case of shallow foundations, the resistance is at the base of the footing only. The side soil mass, whatever the soil mass above the base of footing, that strength is going to be neglected. That strength is going to be neglected. Whereas in the case of the piles, if this is a load I applied, the load is going to be resisted by sides and the load is going to be resisted by base. This is sides and this is a base. I'll show you the pictures, wait for that. So now my question for you is, my dear student, if the resistance offered is going to be more, then you can apply more, then you can apply a large structure also. Yes or no? If the soil is going to be offering less resistance, then you cannot construct the heavy structures. But if you go for the deep foundation, mind it, not only at the base, this is a base. not only at the base, but also side resistance is also going to be there. So I can write one point over here as note. Pile foundations has more load carrying capacity than shallow foundations due to side resistance. Due to side resistance. Keep that in your mind. Pile foundations has a more load carrying capacity than the shallow foundations due to side resistance. So whatever, this is nothing but base, and here there is a sides. But in the case of the shallow foundation, side resistance is neglected. So my dear student, you tell me, as a pile foundations has more load carrying capacity, we do construct large structures on pile foundations and small structures on the shallow foundations. Now let's see what are the different type of the foundations. Means in the case of shallow again. In the case of shallow foundation, again, we are going to divide this into two types or three types. Okay, fine. Spread footing, combined footing, raft foundation. Spread footing, combined footing, raft foundation. And this spread footing is further divided into isolated footing and strip footing. And this combined is also going to be called as again in the combined, or one more footing is there. So strap or cantilever footing you say. So this is going to be strap or cantilever and raft foundation. See, in the case of the shallow foundation, there are different type of footings. Spread footing, it can be isolated or strip, and combined footing. In the case of the combined, it can be rectangular or trapezoidal. So these are the different type of the footings in shallow foundations. Whereas in the case of the deep foundations, we discussed about number one, pile foundations, well foundations. We call it as caissons. Caissons means well foundations and drilled piers. So these are the basic foundations, shallow foundation and deep foundation. Sir, can you please tell us how does these foundations look like? Now, I hope you understood what is the meaning of the foundation and what is the basic difference between the shallow foundation and the deep foundation. And then I gave you the different type of the foundations over here. So now I'll be showing you the figure. You please observe over here. Whatever this is nothing but individual footing, means isolated footing. I hope you understood over here. You see, this is a column, and through the column, whatever this is nothing but the base of footing or not. So I hope this is nothing but isolated footing, and whatever you see, wall footing, or you can call it as a strip footing. Wall footing, or you can call it as a strip footing. So this is a wall. Generally, we do construct this one for retaining walls. Look, in the case of the residential building, so this is for the example as a residential building. Generally, we go for the individual footing. And now you see, whatever this representation is nothing but a retaining wall or strip footing. Strip means, you see, width is going to be, and this is going to be length. So in the case of the strip footing, I say the length is going to be very larger than the width. Then we call it as a strip footing. You know that in the case of retaining wall, the length of the wall is going to be more, length is more, and width of the wall is going to be less. And this is known as a combined footing, which is going to be a rectangle. See, all these representations are isometric projections. I hope you understood. So in this, I can represent if this is a footing, and you see this is one column and this is going to be one column. So these are known as a combined footing. And this is a column load and this is a column load. These two columns are going to be represented with a combined footing, generally preferred when construction space is less. When the construction space is going to be less, then we are going to prefer this. So similarly, there is a one more footing known as a combined. So now you see, I explained spread footing, isolated strip, and in combined rectangle and trapezoidal. So this is also going to become as a combined footing. Now combined strap or cantilever. Now you see, you observe this portion. This is going to be a strap. Whatever, this is nothing but the strap. Sir, how does this look, sir? This strap is going to be looks as, you observe, this is one footing, this is one more footing. Now in between these, if I construct the footing like this, you see, so then this is going to be strap or cantilever. This is known as strap or cantilever. Just like, see, all the combined footings are going to be used when preferred when the construction space is less, then only you go for the combined footing. Either it may be rectangle or trapezoidal or strap, means cantilever. So this is nothing but the strap, which is nothing but a cantilever beam. And you see, whatever, this is nothing but a raft foundation or mat foundation or raft. Sir, what is the meaning of raft, sir? Raft means, you see, for an individual footing or isolated footing, one column. You see, one column, one footing. And in the case of the combined, we go for two footings. So you go for two columns as a single footing. And if you are going to construct all the columns on a single footing, this is a single footing. So which means all columns on single footing. Then we go for the raft foundation. Sir, can you please tell us example? The example is in the case of the black cotton soils. In the black cotton soils are expansive soils. We go for the raft foundation. I'll be discussing the things lateral, means I'll be explaining to the comparison also, but I want you the pictorial representation that how these footings are going to be looks like. And now whatever, this is nothing but a column. This is going to be column, and whatever, this is nothing but a raft or pile cap, and below that whatever you see, this is nothing but the piles. You know, this is nothing but a ground level, and below the ground level also you can observe the piles. So if you observe this figure, if you observe here, whatever this red I am showing you, that's nothing but the pile over here. Okay, so the pile foundations we are going to use mostly, in the case of loose and weak soil masses. So Grilles foundation, floating foundation. Floating foundation is nothing but a pile foundation. Grilles foundation is that's too much. That's not going to be seen now. That is going to be very highly heavy loaded structures. So for the your undergraduation level, it is not going to be important. Whatever I say, see, I refer different textbooks. You don't need to worry about that. If it is important for you, then definitely I would have mentioned it. If I don't mention, which means that's not important for your UG or for your GATE examination. Now, let me show the figures. So, my dear students, what is this? This is nothing but a isolated or individual footing. Whatever, this is nothing but isolated or individual footing. So, I hope you understood this. And you know, this is nothing but see, single footing, 2 columns, combined rectangular footing. I'll show you the figure also, and you see this is nothing but strip footing, because along the length of the wall you are going to provide the footing. Along the length of the wall, this is nothing but load bearing wall. What is the load bearing wall, sir? See, in the case of the basement slab, I hope in the case of the basement floor, if you have ever been saw, if there is a basement floor, especially for the public buildings or commercial buildings, there is a basement floor, right? So there you are going to provide the footing along the length also. And now, my dear students, can you see this one? This is going to be a combined footing. You observe the space between these two is going to be less. The space is going to be less. As the spacing is going to be less, then we go for the combined footings. Now, this is nothing but a raft foundation, as I told you. So whatever this entire area, whatever the plinth area, you see, this is one column, this is one column, this is one column, and this is going to be one more column. All the columns, for all the columns, you are going to provide a single footing. This is known as a raft or mat foundation. And now you can observe, see, this is going to be strap or cantilever. And you see again over here, this is one footing, this is one footing. Again, this is going to be strap or cantilever. So these are the type of the foundations that we see. But for this also you are going to ask very complex topic. Okay, fine. I think you people, means some of the people might think 2 + 2 = 4. That is going to be simple topic. 2 × 2 is equals to 4. that is going to be complex topic for you. Huh? What's there in it? Yeah, I did not start the topic also, but I am saying you what are the different type of the foundations. Yeah, plinth beam is also nothing but this plinth beam, whatever the is a plinth beam, and the plinth beam is nothing but over here as a cantilever or strip footing. Okay, so here, so now this is nothing but the strap or cantilever. Now, so I have shown you different type of the foundations, and let me add how where give me a minute. So I hope means this figure is not that much clear, but I can say the bridge piers would be there or not. So in the case of the bridge pier foundation, whatever you see, this one is nothing but the pile cap, and these are nothing but the piles. So these are the different type of foundations. Machine foundation, grill days foundation, you don't require, Baba, so don't worry about those. So I hope you understood this type of foundations. So you see all these things in reality, right? Now, the condition is, let's go back over here. Okay. So now there are some note points to be remembered. Okay. Basically, listen. Basically, we do prefer the shallow foundations as a isolated foundations mode. Isolated foundations mode. See, this is isolated foundation, and here I represented the raft foundation. Okay. See, you know the meaning of isolated and you know the meaning of the raft. But when do you prefer raft? When do you prefer the isolated foundation? Now, raft or mat foundation is preferred for A, to reduce uneven or differential settlement, settlements. Sir, what is the meaning of uneven or differential settlements? Look, if I say, if the footing is going to be settled, see, if you observe here, this is a footing number 1 and this is footing number 2. If there is a difference in the settlement in the footing 1 and 2, then that is known as a differential settlement. Which means if footing 1 so earlier now see, these are the two footings that I have constructed. Observe. So earlier these two are going to be at the same level. Please observe. So if these are going to be the ground level, they are Now they starts to undergo settlement. Now they starts to undergo settlement. So when they starts to undergo settlement, they starts to undergo settlement, you see, if you observe, see, this is initial condition 1, and the soil below this will starts to undergo settlement. So from 1 to 2. I hope you understood. So due to this load, the footing will undergo some settlement. Now, similarly here also, if you observe over here, the footing is going to be settles up to this point. So I hope you understood what is happening exactly here. So due to the loads, if you observe, the footing has been lowered, and if you see here and here, whatever the difference between these two, whatever the, okay, fine, I'll show much more clear. Just showing you. So whatever this is the base and this is the base, whatever this is known as a differential settlement. Differential settlement. But if you go for, this is isolated foundations or not, if you go for the single foundation, means if you go for the raft foundation, you see, if you go for the raft foundation, when they settle as a whole, as uniform. So in the case of the individual footings or isolated footings, there is a possibility one footing, this is the footing number 1 and this is the footing number 2. So there is a difference in the settlements undergone by the footings. And whatever the difference in the settlements is going to be differential settlement. This is one point. And B is when total area of isolated footings exceeds 50% of total construction area. So whenever the total area of the isolated footing, you take whatever this is the footings are not, so it has one area, second, third one. For example, there are 10 isolated footings you want to construct. Each has an area. 10 into each area. If that total area of the footings, isolated footings, is more than 50% of the construction area, then it's better you go with the raft foundation. Then it's better you go with the raft foundation. So these are the two conditions when we are going to discuss about raft or mat foundation is preferred to reduce uneven or differential settlement, or when total area of isolated footing exceeds 50% of total construction area. Then next, coming to the minimum depth of foundation. Minimum depth of shallow foundation. A, for normal soils, 0.5 to 0.8 meters. For normal soils, 0.5 to 0.8 meters. What is the meaning of this minimum depth of the foundation? You know, whatever, this is nothing but the depth of the foundation, right? Yes, D. And for the normal soils, it is going to be 0.5 to 0.8 meters. Generally, we go for 0.5 meter. So 0.5 meter means, you tell me. So a 0.5 meter, 1 meter is how much? 3 feet, right? 1 meter is nothing but 3 feet. So 3 feet, 0.5 meter means 1.5 feet. So the minimum depth of the foundation is going to be 1.5 feet, which is going to be 0.5 meter to 0.8 meter. And for expansive soils, 2.5 to 3 meters. In the case of expansive soils, high swelling and shrinkage. Look, in the case of the expansive soils, okay, so 2.5 to 3 meters, high swelling and shrinkage. So now in the case of the expansive soils, why we go for 2.5 meters, sir, is, Baba, if you construct your structure on a black cotton soil mass at a depth of 0.5 meters, in the top of 0.5 meters or 2.5 meters, what happens is swelling is more. So now if you construct your structure, black cotton soil mass, if you construct your structure on a black cotton soil, the footing will bulge, means due to swelling of the soil mass, the footing will lift up. When your footing lift up, then your ground floor will behave like a first floor. And during shrinkage, what is meant by shrinkage? Reduction in the volume or not? In black cotton soil, due to shrinkage, the structure will be sucked to the bottom, which means your ground floor will behave like a basement floor. So if you do construct a normal structure on a black cotton soil with a 0.5 meters, then you construct with only ground floor, one floor, and your construction is going to be behaves like a 3 floors: ground floor, first floor, and basement floor. It's very good, right? With 1 floor construction cost, you are going to be believe and behave and live in 3 floors. So do try it. And the type of foundation depends upon the type of soil and type of loading conditions. It is going to be varies from place to place. So that's the reason why I'm not going to say exactly rafter foundation is going to be used in this place, in this time. So these are the conditions. Now, this we need to look over for the foundations. Now let me go for the shallow foundations. See, I discussed the topic with the foundation, and then I said the shallow foundations and deep foundations. What are the type of shallow foundations? These are the type of shallow foundations. And this is going to be the deep foundation. And these are the figures that you have, means in reality. Okay. Now, what is a general requirement for a foundation? General requirement for foundation. So the general requirement for the foundation is, number 1, no shear failure, which means soil should not undergo shear failure. And second one is no excessive settlements. No excessive settlements, which means settlement should be in permissible limit. Settlement should be in permissible limit. That's it. Look, sir, what you have done, sir? Now let me join all the chapters, sir. I'll ask you, you please tell me. In chapter number 7, what we have learned? Chapter number 7, effective stresses. We learned stresses due to self-weight. In chapter number 10, stresses due to external loads. In chapter number 7 and chapter number 10, we discussed vertical stress due to self weight and external load, and we got to know external load causes some problem to the soil. So in chapter number 11, I discussed that as compressibility, which means when you apply some external load, then the footing will undergo some settlement. You see, when you apply some external load, then the footing will undergo settlement. And now that is known as due to consolidation. So my dear students, in chapter number 11, I discussed, Are Baba, when an external load is applied on a soil, due to consolidation, the footing will settle. Keep that in your mind. That settlement should be in a permissible. Permissible means allowable limit only. It should not exceed beyond a limit. So what are those limits? I'll tell you later at the end of the chapter. Number 2. In chapter number 11, okay fine. Are sir, chapter number 10 mein, we got the stress due to external load. And in chapter number 11, due to that external load, the footing will undergo settlement. In chapter number 13, due to that load, inside of the soil body, there is a shear stress. Yes or no? There is a shear stress. And due to that shear stress, the soil may fail by shear failure or not. So, totally how many stresses we are applying due to external load? Normal stress and there is a shear stress. Due to normal stress, what happens to the soil mass? Settlement. Due to normal stress, what happens to the soil mass? Settlement. I represented this point in chapter number 13. Normal stress tends to consolidate the soil, settlement. Shear stress tends to shearing the soil, shear failure. Okay. So now, my dear student, while you are constructing a structure, whatever the external load that you are going to apply, that load should not cause the soil mass for no excessive settlement and no shearing failure should be there. So this is our criteria, general requirement or criteria for the foundations. Okay, now let's see. Come to the shallow foundations. At first, I'm going to discuss about the shallow foundation. Shallow foundation. So now, in the case of the rafter foundation, in the case of the shallow foundation, how we are going to construct? Have a look, please. Okay. You see, initially, see, please listen to this. This is very, very important topic. If you understand this only, then you can understand better anything. This is a ground level. And now, my dear students, we are going to assume the ground level as horizontal. And I want to construct a footing at a depth, some depth below the ground level. At some depth below the ground level. Now let's take the depth below the ground level. Where is the arrow mark? Where the arrow mark gone? Where is the arrow mark gone? Okay, fine. Fine. So now let's take this is a ground level. Everybody. At a particular depth D, now what is the total stress due to self-weight you are going to see? This is known as gamma D. Yes or no? See, before the construction, whatever the depth D, see, this is the depth where you want to construct the footing, but at this point, now listen to the point. So now I took at a depth D, this is the due to self-weight of the soil. What is the stress that you are going to see? Gamma D. Okay. Now, you want to construct a structure. If you want to construct a structure, first of all, you have to excavate the soil or not? Yes. Now let's excavate the soil. So you see over here, now I excavated the soil up to the same depth D. Now you tell me, at the base of the footing, see, before the construction, at the same level, what is the stress that you are going to see? Before the construction, at the same level, what is the stress? Gamma D. Now, due to excavation, what is the stress? No stress at all. Now, what we are going to do is, we do construct a footing. We do construct the footing. See, this is our footing. First, what we did is we done the excavation and then we are going to construct the foundation. Whatever, this is nothing but a footing or foundation. And then we are going to construct the column. And then we are going to construct the column. So now you see, whatever, this is nothing but the column, right? So now, my dear students, you please tell me, this is going to be the column, right? So column, and whatever the soil mass you remove, right? Whatever the soil mass, see, while you are going to construct, you did an excavation, and when you dig an excavation, the soil mass is going to be removed. Yes or no? And now again, whatever the soil that you have been removed during the excavation, take down the same soil mass and fill the soil mass over here. See, are you going to complete your structure without filling over here? No, right? So what we are going to do is, whatever the soil mass we have been removed, now that entire soil mass is going to be again backfilled over here. So what is this? This is going to be the backfill. What is that? Backfill. And whatever the load that is going to be transferred through the column is going to be capital Q. And let's say the base width of the footing as B. Now, my dear students, look, first initially this was the footing. Initially this was the condition. Now, while we are going to construct the structure, first of all, we are going to excavate the soil. Then you are going to construct the footing. Then you are going to construct the column. And then you are going to backfill the soil. Now, can you please tell me what is the total pressure that is acting at the base of the footing? What is the total pressure acting at the base of the footing is nothing but the pressure that transfers at the base due to the column load and due to the self weight of the soil mass. So, first thing is Q, structure pressures, number one, gross pressure represented with a Q. So can you please tell me what is the total pressure that you can look over here? So come on, if B is the base of the footing, then what is the total pressure Q over here? Gross pressure is, first of all, due to footing, due to load, Q by area of footing plus whatever the self weight of the soil mass. You please, my dear student, initially before the construction, what is the pressure? Gamma D. After the construction, due to structure, Q plus A by footing, and now you neglect the thickness of the footing. You neglect the thickness of the footing. If you neglect the thickness of the footing, then see, compared to the depth of foundation, the thickness is going to be very, very, very small. Generally, the thickness is going to be around some 0.1 to 0.2 meters, means that's going to be 10 centimeters to 20 centimeters. So generally 10 centimeters itself is this much. Yes or no? 10 centimeters. So generally the footing size is going to be 10 centimeters, that you will be learn in your RCC. So there is in one more chapter in RCC footings is there you will learn. Now, by neglecting the self weight of the footing, so whatever this is nothing but the backfill, right? Now if I keep my palm, I can feel the stress due to the external load Q by area of footing plus gamma D. What is meant by gamma D? Self weight of the soil. So what is the gross pressure is? The total pressure acting at base of footing, including self weight of soil, soil mass. Then you are going to call it as a gross pressure. Now, my dear student, sir, you are saying this is gross pressure, na? But before the construction, who are there already? Before the construction, self weight was there, are there or not? Yes or no? And after the construction, this is before the construction and this is after the construction. Before the construction, gamma D. After the construction, Q plus A by gamma D, which means self weight of the soil mass is present before construction and after construction. And due to construction, what is the load that you are going to see extra is nothing but this Q by area of footing or not? Yes or no? So whatever the pressure that you applied by the means of external load means the extra pressure is known as net pressure. The pressure that is going to be acting at the base is known as a net pressure. Repeating again, before the construction, gamma D is there. After the construction also, gamma D is there. Then what is the extra pressure we applied due to structure? The extra pressure we applied is nothing but this Q by area of a footing. And that is known as net pressure. So now second one is net pressure represented with Qn. Net pressure or pressure at base of footing by excluding the self weight. By excluding the self weight of soil is known as a net pressure. So can you please tell me how to find out the net pressure? Whatever the net pressure, Qn is nothing but gross pressure minus gamma d, and this is known as a self weight of soil mass. You know that. So what is the gross pressure? The gross net pressure is nothing but gross pressure minus self weight of the soil. So I hope you understood this too. First, number one is going to be gross pressure, and number two is going to be net pressure. What is mean by gross pressure? Now you see, I am a footing. Whatever the pressure total acting on me, that is the gross pressure. And now, as you know, self weight is acting before and after. Then what is the extra pressure? Net means difference, right? What is the difference in pressure? You please look over here. Sorry, is that isolated or strip footing that you are explaining now? I am explaining the spread footing, whether it is isolated or strip. You don't need to worry. I am explaining a spread footing. Okay, let me explaining isolated only. So for you, for the better sake of your understanding, I am explaining as a isolated. Okay. Now, look. Next one. Soil pressures. So far and so good. I explained whatever the stresses acting at the base. You see, at the base of footing and at the base of footing. These are the stresses acting on the soil. Now, my dear student, you listen. I am a soil mass. Whatever the pressure you apply on me, that is nothing but the gross pressure. And if you remove the self weight of the soil, then it is going to be the net pressure. But whatever the pressure you applied, that should depends upon me or not, which means if I am able to take, then only you can apply that, yes or no. Which now, what is the pressure exerted by the soil upon the footing? Means what is the capacity of the soil mass? See, I am a soil, I have some capacity, right? And when you apply some load, what is the capacity of me to take that load? That is known as a soil pressures. We call it as a bearing capacity. So there comes. You might thinking about the chapter number 16 name as bearing capacity. So there comes the bearing capacities. So now you see, what is this bearing capacity? What is the bearing capacity? Number one, ultimate bearing capacity of soil. Ultimate bearing capacity of the soil. Number one. So this is going to be represented with QU. What is the ultimate bearing capacity of a soil, sir? So my dear students, you tell me, what is meant by ultimate bearing capacity? Ultimate maximum. What is meant by ultimate maximum? So I am the soil. Whatever the pressure you apply, total pressure, what is the maximum that I can take without any failure is known as ultimate bearing capacity. So maximum gross pressure that a soil can bear or take without any shear failure. Without any shear failure. So whatever the maximum gross pressure, this is the gross pressure or not, whatever the maximum gross pressure that you can apply on me, without any failure, that is known as my capacity. For example, if I say my capacity is 100 kilopascals, my capacity is 100 kilopascals. What is the meaning of 100 kilopascals? The maximum pressure, gross pressure that we can apply on me is 100 only. If you apply more than 100 kilopascals, then definitely I am going to be failed. Yes or no? So ultimate bearing capacity of the soil, QU, maximum gross pressure that a soil can bear or take without any shear failure. Okay? Okay, fine. Sir, my question for you, sir. Which one is responsible for the failure, gross pressure or net pressure? Think. Which one is responsible for the failure of a soil mass, gross pressure or net pressure? What is meant by gross pressure? Self weight of the soil plus external load. What is meant by net pressure? Only external load. Yes. Does self weight causes any failure to the soil? No. The pressure that causes failure to the soil is going to be net pressure. The pressure that causes failure to the soil is going to be net pressure. Now, as you know, see, let's say I'm giving an example over here. Already gamma D is 50 kilopascals, and due to the structure, the gross pressure is going to be 150. So gross pressure 150 minus self weight 50. If you remove, what is the net pressure? 100. And you have to apply that net pressure in such a way soil should not fail or not. Now, let's see. Second one. Net ultimate bearing capacity. Net ultimate bearing capacity, QNU. Look, see, in the gross pressure there is a self weight, and I don't need to worry about the self weight, because who is responsible for the failure? External load. So what is the pressure caused by the external load? Net pressure. Yes or no? Now let's say you are applying some 100 kilopascals of net pressure. Then what is the maximum net pressure that I can take without any shear failure? Maximum. Ultimate means maximum. But this time, is it a net pressure or gross pressure? Maximum net pressure that soil can take without any shear failure. And how you are going to find out it, sir? The net pressure, net ultimate bearing capacity is nothing but ultimate bearing capacity minus gamma D. Because what is the meaning of net? What is the meaning of net? Net means you are removing the self weight. Net means by excluding the self weight. For example, now listen everybody. My ultimate bearing capacity is 150. My ultimate bearing capacity is 150, which means, see, already let's take this gamma D as a 50. Let's take gamma D as 50. Now my ultimate bearing capacity is going to be 150. What is the meaning of 150? Okay, I can take the total maximum pressure up to 150. But out of that, already 50 is going to be whom? Self weight. I take maximum 150. Out of that, already 50 is due to whom? 150 is due to whom? Self weight. Then, due to external load, what is the maximum that I can take? Only 100, right? I have 150 capacity, and out of 150, already I took 50 from the self weight. Then how much remaining? 100. Which means I can take the external load maximum up to 100 only. That is known as net ultimate bearing capacity. Maximum net pressure that soil can take without any shear failure. That is known as net ultimate bearing capacity. Now, are you going to design for critical condition or safe condition? Are you going to design for critical condition or safe condition? We always design for the safe condition or not? When you go for the safe condition, we have to apply the factor of safety. So net safe bearing capacity represented with a QNS. So you please observe the terms I am using. Ultimate maximum gross pressure, net ultimate maximum net pressure. Now I am not discussing about the maximum, I am discussing about the safe. So the net pressure that a soil can bear, that a soil can take safely without any shear failure. Without any shear failure. So now everybody, what is the QNS? QNS is equals to, see, maximum net pressure that I can take is 100. I say to you, my dear student, I'm a soil mass, and if you apply some external load, the maximum pressure that I can take due to the external load is 100. Now you tell me, are you going to apply exactly 100? Are you going to apply exactly 100 or less than 100? See, I said my maximum strength, and while you are designing, you have to design in such a way, you need to keep the future forecasting also. In future, there may be earthquake loads, there may be wind loads. So if you apply exactly 100 on me, in future, the load would be more than 100. My capacity is 100. If the load is more than 100, soil will fail. So while you are going to design, are you going to apply the load exactly the maximum load or safe load? Safe load. So what we are going to do is we are going to apply the factor of safety for the net ultimate bearing capacity. And this factor of safety is going to be around 2.523. This F means factor of safety. So my dear student, this is safely and this is maximum. Please understand the differences. So at first I said the ultimate and net ultimate, and what is the maximum pressure that the soil can take is nothing but net ultimate bearing capacity, and now it is going to be net safe. So what is the meaning of the net safe bearing capacity? Please tell me. You are a soil, imagine yourself. What is the meaning of net safe bearing capacity of you? The pressure that you take safely without any shear failure. That is known as net safe bearing capacity. Now, safe bearing capacity. QS. Safe bearing capacity. You see, ultimate to net minus gamma D. Net to safe means gross safe bearing capacity. Now I can simply add upon QS is nothing but QNS plus gamma D. QNS plus gamma D. So this is the safe bearing capacity. Listen everybody, what I have done is finally you see this is ultimate bearing capacity, right? Yes. In the ultimate bearing capacity, first I am removing the self weight, and then I am applying the factor of safety for that, and then I am adding the self weight, which means we are not adding any factor of safety to the gamma D. We are not doing any safety factor for the gamma D. Why, sir? Sir, I'm telling you again, sir, failure is due to external load, not the self weight. So as the failure is external load, you have to take the pressure due to external load as a net pressure. And what is the maximum that you can, what is the safe you can take without any shear failure is known as a QNS. So out of all the pressures, can you please tell me which pressure is going to be minimum pressure? out of all the pressures, which pressure is going to be minimum pressure? Come on, QU, QU, QNU, QNS and QS. Which one is less pressure? QNS. So my pressure is going to be less pressure as QNS. And for no failure, whatever the net pressure you apply should be less than or equals to net safe bearing capacity. In the four failures, in the four stresses, means in the four capacities I discussed, QU, QNU, QNS and QS. I discussed about shear failure only. But what is the general requirement? For no shear failure and for no excessive settlement also, right? No. Fifth one, net safe settlement pressure represented with QNP. Net safe settlement pressure. This is net safe bearing capacity and this is net safe settlement pressure. Now define what is the meaning of net. Net pressure that a soil takes safely without any excessive settlement. Without any excessive settlement. Okay. So now you see at first I have been discussed about the shearing failure. So let's go back once again. Everybody have a look. Everybody have a look. What is the total pressure acting at the soil mass? Q, which is nothing but net pressure plus self weight of the soil. Okay. What is the total pressure? Net pressure means external load and gamma D means self weight. And what is the maximum? See, you apply Q. And what is QU? QU means the ultimate bearing capacity of me. Now, my dear student, let's take an example. I have completed. So now let me say I'm a soil over here. My ultimate bearing capacity is going to be 200 kilopascals. My ultimate bearing capacity is going to be 200 kilopascals. What is the meaning of that? What is the meaning of that? This is a soil. The soil, what about the soil mass? This is a ground level at a particular depth. So you construct the structure. The ultimate bearing capacity is going to be 200 kilopascals. Just imagine. What is the meaning of this 200 kilopascals? Whatever the pressure you applied on the top, that this soil will be take a maximum of 200 only. Maximum of 200 only. And let's take gamma D as 50 kilopascals. Let's take gamma D as 50 kilopascals. Now, Hare Baba, this 200 in this 200 already the soil is bearing the soil mass whose self weight is going to be 50. Whose self weight is going to be 50, which means the net ultimate is going to be 200 minus 50, which is going to be 150 kilopascals only. So, due to this external load Q, the maximum stress or the maximum pressure that a soil take without any shear failure is 150. So now I say that to you, soil T for no failure. Are you going to apply exactly 150? No, right? You are going to apply some factor of safety. and that is known as net safe bearing capacity. 150 by, let's take it as 3. Let's take it as 3. What is the meaning of 3? 50 kilopascals. What is the meaning of 3 here? Factor of safety. So, at first I am telling my ultimate bearing capacity, and then I am saying, array, my capacity, already I am taking some self weight. I remove the self weight, then that is going to be net ultimate bearing capacity. But I say to the engineer, even though my strength is 150, am I going to ask you to apply 150? No, right? I'm going to ask you, you have to apply the load less than the actual. So I am going to apply the QNS as a 50. What is the meaning of QNS as a 50? What is the meaning of QNS of 50? Whatever the soil mass, the net pressure that this soil can take, whatever the net pressure means QNR not net pressure, whatever the net pressure that the soil can take without, means safely, without any shear failure, should be equals to 50, which means whatever the pressure you apply should be less than or equals to 50. So I hope you understood this. Now, sir, you are saying one is net safe bearing capacity and other one is going to be net settlement, net means without any excessive settlement. But what is the general requirement for foundations? The general requirement is there should be any shear failure, there shouldn't be any excessive settlement. I don't want any shear failure or any settlement. So which one I have to take? Now the last one is sixth, net allowable pressure. Net allowable pressure represented with QNA. So what is the meaning of this, sir? The net pressure that soil can take safely without shear failure and excessive settlement. Look, whatever the pressure that the soil can take without any excessive settlement is QNP, and without any shearing is going to be QNS. So now I want without any shear failure and without any excessive settlement. Can I say an example? Let's take QNS as 40, QNP as 50. Let's say QNS as 40 and the QNP as 50. So everybody, tell me please, what is the meaning of QNS as 40? What is the meaning of QNS as a 40? Think. What is the meaning of QNS as a 40? The meaning of QNS as a 40 is equals to, I am a soil mass, my QNS means my net safe bearing capacity is 40. So up to 40, if you apply up to 40, I am safe against the shear failure. I am safe against the shear failure. Now what is the meaning of QNP 50? So up to 50, the net pressure you apply, up to 50, I am safe up without any excessive settlement. But if I apply 50, what happens? If I apply 50, then the soil is safe in excessive settlement, but this 50 is more than 40 or not? What is the meaning of 40? Without any shear failure up to 40, without any excessive settlement up to 50. If you apply 50, then the soil will fail by shear because QNS is going to be small, right? But if I apply 40, soil will be safe in shear. At the same time, as a 40 is less than 50, for up to 50, soil is safe in settlement, and as it is 40, soil will be obviously safe, which means out of these two, if I take the smaller value, if I take the smaller value, then soil will be safe in both the shearing and excessive settlement. So now what I want to say here is, this QNA is smaller of QNS and QNP. So that's the final condition. See, we have been discussed about the soil pressures and the pressure from the structures. And now ultimately, whatever the footing we have, this is the net pressure and this is going to be the net allowable bearing capacity. What is meant by net allowable bearing capacity? Definition: the net pressure that soil can take safely without a shear failure and without any excessive settlement. Without shear failure, without excessive settlement. So now the design condition. The design condition is at the base of the footing. This is a net pressure and this is net allowable bearing capacity. Keep in your mind, Qn is always less than or equals to Qna. So this is the design condition. This is the design condition. So Qn is going to be always less than or equals to Qna, where Qna is smaller of Qns and Qnp. So my dear students, you please observe, this is the last point with this I will be concluding, means whatever this topic. In case, look and listen. In the case of clays, when you apply load, say I said you chapter number 10, if you apply load, vertical stress is there. Chapter number 11, we discussed about consolidation settlement. Chapter number 13, we discussed about the shear. So in the case of clays, if I apply load, which failure will occur first? Settlement failure or shearing failure? Think and say. Think. In the case of clays, which failure will occur first? Does a shear failure occur or settlement failure occur? Think and say, please. I am asking you which failure will occur first. Tell me which failure will occur first. Settlement, shear, settlement, shear. Most of the people are settlement. Okay. Can I ask you one question? You means you stop? I'll ask one question now. Okay. Fine. Stop. Okay. I'll ask one question. In the case of clays, does settlement occurs quickly? Does settlement occurs within a time? You know that in the case of clay, permeability is very less now. When the permeability is very less, the amount of water to dissipate, the time required to dissipate the water is going to be large, which means in the case of the clays, settlement is more, but the settlement rate is very slow. In the case of clays, settlement occurs over longer period of time, and during this longer period of time, the soil would be failed by means of shear. So in the case of clays, as settlement happens over long time, shear failure occurs at first. And now, whatever the stress required for the shear failure, QNS is less than QNP. What is mean by QNP? Excessive settlement, right? As settlement is going to be takes over longer period of time, it won't undergoes excessive settlement that much easily. I told you in the case of the leaning tower of Pisa, it leaned over years and years and years. Yes or no? So how many years it has been leaned? But it has been failed by shear failure also beneath that. So in the case of clays, so now QNA is equals to QNS. QNA is equals to QNS. So in clays, this is happens in the case of clays. Now, in sands, settlement occurs quicker than shear failure. So here QNP is less than QNS. So QNA is equals to QNP. So QNA is going to be less than QNP. I hope you understood these 2 points. So this was one of the previous ESE questions only. In the case of clays, which failure occurs easily? Shearing failure. So you have to design for whom? No shear failure. And in the case of sands, which failure occurs easily? Settlement failure. So you have to design for no settlement failure. Okay. And the final conclusion. Generally, most of the soils fails by shear only. Generally, most of the soils fails by shear only, which means QNS is less than QNP. And as I said you, the net allowable is going to be equals to QNS. Then the design condition is QN should be less than or equals to QNS. What is the meaning of QN? Net pressure acting on the soil. What is the meaning of QNS? The net pressure that the soil can take without any shear failure. So always that net pressure should be less than or equals to QNS. So I hope you understood this. Now what I do is, for this one, for the same thing, if I add gamma D on both sides, so if I add gamma D on both sides, now you tell me what is the net pressure plus self weight? Gross pressure means, net pressure means gross pressure minus self weight, right? So can I write the net pressure plus self weight is nothing but the gross pressure is going to be less than or equals to, what is the net safe bearing capacity plus gamma D? Safe bearing capacity. So this is the final condition that we have to apply. Look, until or unless they mention soil failed by settlement, you always take this is going to be there. So generally most of the soils fails by whom? Shear only. In question they will ask you clearly factor of safety against shear or soil fails by shear. When I say shear happens first than the settlement, which means the pressure required for shear failure is less than the pressure required for the settlement failure. So net allowable is nothing but QNS. Because of the smaller one, then the design condition is going to be Q less than or equals to QS. I hope you may have seen in RCC, for every foundation question, there is SBC of soil. What is SBC? Safe bearing capacity of the soil. Whatever the safe bearing capacity of the soil mass, SBC, is nothing but QS. I'm going slow only. So with this, I have completed the design condition for today. Yes. So I hope you understood the type of pressures. Ultimately, Nana, you keep one thing. Soil mass should not fail by settlement and shearing. What is the minimum pressure that the soil can take without any shear failure is nothing but QNS. QNS. So that's the net pressure that a soil can take without any shear failure. And what is the net pressure that a soil can take without any excessive settlement is QNP. Sir, how we are going to determine all these things we will be seeing tomorrow. That depends upon the ultimate bearing capacity that we discuss tomorrow. But as of now, you just focus on the terminologies. So once I send the notes to you, within no time, you please go through the notes once again. And see, there is no doubt session today also because I'm having a lot of headache. So my head is banging like anything from the past 1 hour. But I don't want to stop the class, so I continue with the class. And it's already 1:12, so we'll be seeing the doubt clearing session tomorrow. Okay, so with this, today's session will be done. You please go through the notes once again. I have given you all the practical examples over here also. So please go through this. And for today, I'm stopping the session here itself. So I hope you people understood. I hope you people are able to understand. So if any problem, let me know. If there is any problem, let me know. Yes. So those who wants to leave, they can leave. And if there is any problem, please let me know. I'll be here. Yeah, whatever the doubts, please, if you have any doubts, so today I'm not going to discuss those. And if you send me the mail, I can see that. Sir, use eucalyptus oil for headache, it will be effective. Thank you, dear. Thank you very much. What is the disadvantage of raft foundation? There is no, that is the disadvantage of raft foundation is it's uneconomical. Cost is going to be more, that's it. Okay, so I'll be leaving the session today. Have a great day.